So we're going to analyze the function 4x over x squared plus 1 and make an accurate sketch of this function. First thing we should do is figure out our domain. You can see that the denominator of x squared plus 1 actually will not have any zeros, any real zeros. Okay, so we're not going to have any vertical asymptotes. So in fact, the function will be continuous on XER. So that's the first analysis. Now the second point is we should figure out any intercepts. Okay? So to figure out any y-intercepts, we need to set our f of x equal to 0. And when we do that, that's really making the numerator equal to 0. So for the y-intercept, we want 4x to equal 0, which means that x is equal to 0. And if this is the case, then it turns out that this is the only x-intercept as well. Okay, or sorry, the x and y-intercept. So let me put my scale down, and then we can start plotting some points. So 0, 0, first of all, there it is. So in this case, the y-intercept happened to be the same as the x-intercept. Okay, now let's move on to figuring out the first derivative. Okay, if you want to use the function written as is, then you're going to have to apply quotient rule. Otherwise, you can change x squared plus 1 to be bracket x squared plus 1 close bracket to the negative 1, and then use product rule instead. That's up to you. I'm just going to use quotient rule. So derivative of 4x is 4 times x squared plus 1 minus 4x times derivative of x squared plus 1 is 2x divided by x squared plus 1 squared. Now I'm going to get 4x squared plus 4 minus 8x squared over x squared plus 1 squared. And then I will end up with a negative 4x squared plus 4 x squared plus 1 squared. And for the purpose of finding our second derivative later on, just to make it a little bit easier on us, I'm just going to factor out that negative 4 and just leave it in this format. At this point, I want to figure out where my critical points are, and the critical points are going to exist where f prime is equal to 0, which means that my numerator has to equal 0. So if negative 4 is just a coefficient, so we don't have to include that in our equation, right? We just want to make sure x squared minus 1 equals 0, and then that means that x equals plus or minus 1. And when we take a look at the denominator equaling 0, that's when f prime will not exist. But we can see that when we make x squared plus 1 squared equals 0, there aren't going to be any real answers anyway. Okay, so our only possible critical points are going to be at positive and negative 1. At this point, it's up to you whether or not you want to do the number line. I am going to use it just to have a clear idea of whether my function is increasing or decreasing. If you just want to use the second derivative to figure out if you have a local max or a local min at these points, that's fine as well. Okay, when I take a number that is smaller than negative 1, I square it, and then I subtract 1, that's going to be a positive answer, times negative 4, that'll be negative. I don't have to worry about the denominator, it's always going to be positive regardless. Between negative 1 and positive 1, a number like, let's say, 0, then that's going to be negative times negative, so it'll be positive. And then a number greater than 1, so positive, negative, overall, negative. So the function is going to be f of x will be decreasing, then increasing, then decreasing. So that should tell us that we are going to have a local decreasing to increasing, so local minimum at -1, and then increasing to decreasing, so local maximum at x equals 1. So if we want to write down here, we have our local minimum at f of -1, which is going to be -4/2, so -2. And then we will have a local maximum at f of 1, which is going to be 4/2, so +2. So we can plot those points down. -1, -2, and 1, 2. There are our local max and min points. So let's continue. Now we're going to figure out the second derivative, and that will help us figure out the intervals of concavity and see if there are any points of inflection. So for the second derivative, leave that -4 coefficient on the outside. Derivative of x squared minus 1 is 2x. Leave x squared plus 1 squared alone, and then minus x squared minus 1 times, you're going to have to apply chain rule here, 2 times x squared plus 1 is the exponent of 1, multiplied by the derivative of the inside, which is 2x. Then all of that over x squared plus 1 squared. Okay, so now let's see, we have a 2 and an x squared plus 1 here. We have a 2 and an x squared plus 1 here, so we might as well factor that out. Okay, so then we are going to be left with x times x squared plus 1 minus this 2x times x squared minus 1. All of that over x squared plus 1. Oh, sorry, this should be to the exponent of 4, not 2, so let me fix that. There we go. And now we can cancel out x squared plus 1 with one of the x squared plus 1s in the denominator there. And then when we simplify this numerator, we will get inside x cubed minus 2x cubed, so negative x cubed, and then x plus 2x, so that's plus 3x, over x squared plus 1 to the exponent of 3. So really, I can simplify this to, I can take out another negative x and then multiply it with this negative 8, so it'll be positive 8x, and then x squared minus 3 over x squared plus 1 cubed. So this is my second derivative. And now I want to figure out where the second derivative is 0 and where it does not exist. So the second derivative will equal 0 when the numerator is equal to 0. So 8x, x squared minus 3 equals 0. So that means I will have 2 points at x equals 0 and at x equals plus minus root 3. So these are my three possible points of inflection that I will need to create a number line or interval table for and check. Okay. And again, if I take a look at this denominator and I try to see if there are any new points where the second derivative does not exist, it turns out that I still will not have any real answers for this expression. So I'm going to just create my number line or interval table to figure out the concavity. Root 0, root 3. And this is for the second derivative, whether it's positive or negative. So I can just plug in some test points into the second derivative equation to figure out whether my intervals are positive or negative. And it turns out that we are going to end up with the following: negative, positive, negative, and positive. So because of that, we can conclude that the original f of x function should be concave down when x is less than negative root 3, concave up from negative root 3 to 0, concave down from 0 to root 3, and then concave up when x is greater than root 3. And furthermore, because of the sign changes going on here, we can conclude that we actually have 3 points of inflection. Okay? So one of these points is going to be at 0, 0. Another point of inflection, you plug in x equals negative root 3 into the original function. So you're going to get negative 4 root 3 over 3 plus 4. So negative root 3. And then the last point of inflection, when you plug in root 3 into the original function, 4 root 3 over 4, so it'll be root 3, root 3. Okay? So now that we have these points of inflection, we can also graph them. For the purpose of plotting, just make sure that you know that root 3 is approximately equal to 1.73. So a little bit easier to plot your points that way. Negative 1.73, negative 1.73, right around here. And then positive 1.73 and positive 1.73, so right around there. Those are my points of inflection. In order to complete the sketch of the function, because it is a rational function, I should check to see what kind of other asymptotes there are. We know that there aren't any vertical asymptotes because the denominator will never equal 0. However, when we analyze the degree of the numerator compared to the degree of the denominator, we should see that we do have a horizontal asymptote. So our horizontal asymptote is going to be y equals 0, since the degree of the numerator is less than the degree of the denominator. Okay, so I can show my horizontal asymptote going across y equals 0. And I know that there aren't going to be any crossover points because when I tried to put in y equals 0 to solve for x, the only possible value was x equals 0. So I know that this part, when x is greater than 0, this part of the graph has to lie above the horizontal asymptote at all times. And when x is less than 0, the graph has to lie below the horizontal asymptote at all times. And there's the sketch of my function. Concave down, concave up, concave down, concave up. We have our local extrema at negative 1 and 1. We have our points of inflection at negative root 3, 0, and positive root 3. We have our x and y intercept, and we have our horizontal asymptote. Okay, let's move on to the next example. Okay, for this example, we have the function x squared over x minus 1. So the first thing we are going to do is to figure out that the function is not continuous. We will have a break in the graph at x equals 1 because that is the 0 of the denominator. So our vertical asymptote will lie at x equals 1. So let's get started right away, plotting some features. Okay, so there's my vertical asymptote. Let's figure out any zeros or intercepts. y-intercepts that we might have. So I can see that when x squared is equal to 0, I'm going to get x is equal to 0 for my x and y-intercept, and that's it. That's all I have. We can look for, because the degree of the numerator is 1 higher than the degree of the denominator, we know that we're going to have an oblique asymptote. So to figure out our oblique asymptote location, we're going to have to do long division. And we see that, therefore, our oblique asymptote is going to be y equals x plus 1. There was a quotient once we divided. And x plus 1, that's a line with a y-intercept of 1 and a slope of 1. So it's essentially going to be a line that looks like this. So we figured out whatever we can just from the original function equations. So now it's time to look for the critical points. So let's figure out the first derivative. So derivative of x squared is 2x multiplied by x minus 1 minus x squared. Derivative of x minus 1 is just 1. And then over x minus 1 squared. 2x squared minus x squared will be x squared, and then minus 2x over x minus 1 squared. So this is going to be our first derivative, and we want to look for where the first derivative is equal to 0. That's where the numerator is equal to 0. And we have two possibilities, 0 or 2. So that means that this 0, and when x is equal to 2, they might be our relative extrema. And now for the other part, when we look at f prime not existing, that's when the denominator is equal to 0, and that only happens when x is equal to 1. But this would not be considered a critical point, remember, because x equals 1 is already a vertical asymptote. And x is equal to 1 is not in the domain of the function. So really, we just need to focus on x equals 0 and x equals 2 being our local extrema. So this time, I'm not going to use the first derivative test. Instead, I'm going to move on and figure out the second derivative and try to use the second derivative test instead to see whether or not these 2 points will give us local extrema. So let's take the second derivative now. 2x minus 2 times x minus 1 squared minus x squared minus 2x times 2x minus 1 times 1 over x minus 1 to the exponent of 4. There is an x minus 1 that is common to both of the numerator terms, so I will take that out. Then I will be able to cancel out the x minus 1 from the numerator with one of the x minus 1s from the denominator. And then when I expand the numerator completely, this will be 2x squared minus 2x minus 2x, so minus 4x, and then plus 2 minus 2x squared plus 4x over x minus 1 cubed. Okay, and I can see that these terms, 2x squared minus 2x squared, negative 4x plus 4x, they're all gone. So really, the only thing that I'm left with is 2 over x minus 1 cubed. And at this point, we need to figure out any values of x that will give us a second derivative that does not exist, or a second derivative that where the second derivative is equal to 0. So if we try to make the second derivative equal to 0, the only possible way is if the numerator equals 0. But that's not possible. 2 doesn't equal 0. Okay. And then we can see that, just looking at the denominator, the second derivative will not exist when x minus 1 cubed is equal to 0. So that means when x is equal to 1. But again, this can't be a possible point of inflection, because x is equal to 1 is not in the domain of the function. Okay? But we can still use x equals 1 for our second derivative, the number line. So here's our second derivative. When x is less than 1, we want to figure out whether the function is concave up or concave down. And if you plug in a number like, let's say, 0, 0 minus 1 cubed, that's going to be negative. So overall, the function, or the second derivative, will be negative. X is greater than 1, this will be positive. Okay? So that means that the original function, f of x, will be concave down when x is less than 1, and concave up when x is greater than 1. And then going back to where our critical points were, up here at x equals 0 and x equals 2, this is where f of 0 would fall, and this is where f of 2 would fall. Okay, so f of 0 would be negative, and if the function, the critical point at x equals 0, the derivative is equal to 0, and then the value of, the second derivative is negative, then that means that we are going to have a local maximum. And the local maximum at f of 0 will be 0, 0. So let's do the same thing here. For x equals 2, the second derivative is going to be positive. So that means that we're going to have a local minimum at the point 2, 2 squared minus 1. So that's going to be 2, 4. So that's it. We can just plot these 2 points, and that's all the information that we have. So now let's plot 2, 4 on our graph. We already have 0, 0 here. So 2, 4 is here. And now, just to complete the graph, we know that the function is going to be concave down on this interval, concave up on this interval, and usually rational functions hug the asymptotes. So we can safely assume that the graph is just going to look like this. If you want to make your sketch more accurate, you can add in some more points by plugging them into the function and then getting the y values back. The other thing you can also do, if you wanted to check whether or not these points along the oblique asymptote, whether or not they ever cross over, okay, you can check by making your function f of x equaling the oblique asymptote x plus 1, and then solving for any possible x values. So when you do that, though, you will quickly see when we cross multiply here, we get x squared minus 1. This is going to be 0 equals negative 1. This is impossible, right? So that means that there aren't going to be any crossover points. Okay. The other way you could do this, and the textbook shows you, is you can plug in a really large number for x, like 100, let's say. Okay, plug that into the original function, f of x, as well as the equation of the oblique asymptote, x plus 1. See which one is bigger. Okay, it's going to turn out that f of x will be larger for x is equal to 100. So that's how you know that the graph lies above the oblique asymptote. And then you do the same thing for a really large negative number, like let's say negative 100. You plug it in for f of x, plug it into the oblique asymptote, and in that case, the function will be smaller than the oblique asymptote value. So that's how you know that the function will lie below the oblique asymptote at all times. Okay, let's move on to the last rational graph sketch. This time we're going to sketch the graph of, sorry, there should be an f there, f of x equals 2x squared plus 3x minus 1 over x plus 1. Okay, first of all, we know that there's going to be a vertical asymptote at x equals -1 because that's the 0 of the denominator, and we can see that it's not going to be a 0 of the numerator. Okay? And in order to figure out any intercepts, for the y-intercept, let's plug in x equals 0. So that's going to be 2 times 0 squared plus 3 times 0 minus 1 over 0 plus 1. So that'll be 0, -1. And then when we set y equal to 0, that's really just looking for the numerator values equaling 0. So we need to, it's not a factorable trinomial, unfortunately, so we're going to have to use our quadratic formula. -3 plus minus square root 3 squared minus 4ac over 2a. So -3 plus minus root 9 plus 8, so root 17 over 4. And you can use your calculator to estimate what those values are. So approximately 0.28 and -1.78. So let's plot all of these points that we have so far and other features. So let's see, f of 0 is at -1, and then our x-intercepts were at 0.28, so really close here, and -1.78. And because the degree of the numerator is 1 higher than the degree of the denominator, we know that we're going to have an oblique asymptote. So again, we will need to do long division. So that is going to give us our x minus 1. And then afterwards we have +1, so x plus 1, and then subtract, we'll end up with -2. So right here, we have our oblique asymptote of y equals 2x plus 1, which is a line with a y-intercept of 1 and a slope of 2. Let's fill in those values. Or sorry, the dotted line rather. So there's the oblique asymptote y equals 2x plus 1. Oh, and the vertical asymptote as well. I should put that in at -1. Okay, so then I've done all I can with just the function equation. So now let's figure out the derivative. So f prime is going to be 4x plus 3 times x plus 1 minus 2x squared plus 3x minus 1 times 1 over x plus 1 squared. 4x squared plus 7x plus 3 minus 2x squared minus 3x plus 1 over x plus 1 squared. So this is going to give me 2x squared plus 4x plus 4 over x plus 1 squared. Let me just take out a 2 just for ease later on. Okay, so in order to figure out any critical points, I need to see where my first derivative is equal to 0. So that's really where x squared plus 2x plus 2 equals 0. When you try to solve this using the quadratic formula, if you just use the discriminant b squared minus 4ac, you're going to see that it's a negative value, so there aren't going to be any real solutions. Okay. So in fact, the only possible point where the function changes from increasing to decreasing is at your vertical asymptote, because that's where the derivative also does not exist. Okay, but it's not a critical point. It's not going to be a relative max or min, obviously, because x equals -1 isn't contained in the domain of the original function. Alrighty, so let's move on to the second derivative now. So the second derivative is going to be 2 times 2x plus 2 times x plus 1 squared minus x squared plus 2x plus 2 times 2x plus 1 times 1 over x plus 1 squared. Okay, so I see that there's a 2 times x plus 1 that I can take out here as well as here. Sorry, bracket there. So here, when I took out an x plus 1 and then I took out an x plus, or 2 times x plus 1 really from here, so I just have x squared plus 2x plus 1 left from this x plus 1 squared. And then minus, I took this out, so I'm left with this x squared minus 2x minus 2 over x plus 1 squared, or sorry, it's squared, squared, so it's really to the exponent of 4. So now I can cancel out my x plus 1 with the x plus 1 to the exponent of 4. So I will be left with 4 times x squared minus x squared gone, 2x minus 2x gone, 1 minus 2 is -1, over x plus 1 to the exponent of 3. Sorry, that looks weird. So it's -4 over x plus 1 cubed. That's my second derivative. So again, in order to figure out where my second derivative is equal to 0, I would have to make my numerator equal to 0, but there are no solutions for that. -4 can never equal 0. Okay. But I can consider the fact that at -1, my second derivative will not exist. So I can at least use that to help me figure out whether my function is concave up or concave down. Okay, so when I plug in a number that is smaller than -1, like -2, then I'm going to have a negative value here cubed, which is negative. Negative divided by negative is positive. Okay. Higher number than -1, like let's say 0, that's going to be positive. Then negative divided by positive is going to be negative. So that means my overall function is going to be concave up when x is less than -1, concave down when x is less than or greater than -1. And since I didn't have any relative max or min values either, just to strengthen what I know about the function, I can also include my first derivative because that was really on the same number line because x equals -1 was really the only value of significance. And I can see that when x is less than -1, then the first derivative is going to be positive. And when x is greater than -1, the first derivative is still going to be positive. So the function is always increasing. Okay, so based on all of that information, I can say with confidence that my graph is simply going to look like this. And again, if you want to add in some more points, feel free to do so by plugging in an x value into the function, and that will give you some more points that you can plot. for accuracy. For this final example, we're going to be going backwards a little bit. We're given this time some features of a function, and we need to analyze what the graph of that function should look like based on these features. So given this type of question, I would strongly recommend that you create a number line for yourself, just so that you can see what is happening for each of the derivatives. And then that way you can sort of compile that into information about the function itself. So these are the three number lines that I'm going to have, our sort of interval table kind of deal. So here's my first one for the first derivative. So I see that the first derivative is going to be positive when x is less than 0 and when x is between 2 and 5. So I'm going to put 0 here, and then 2, and then 5. So I can say that it's going to be positive, and then positive. And then the only other information I'm given is that the first derivative is negative when x is greater than 5. So for now, I'm going to leave this space blank because I'm not 100% sure what this should be. Okay. But right now, based on this information that's given, I already know one important feature of this function, and that's the fact that if the function was increasing on this interval, then decreasing, then we have a maximum at x equals 5. Okay. And then the other thing is, right, this is confirmed based on the fact that our f prime of 2 is equal to 0 at here, and as well as f prime of 5 equals 0. Okay. So now for this next part here, the second derivative is negative when x is less than 2 and when x is between 4 and 7. So just try to line it up approximately the same here and up here. Okay. So negative when x is less than 2, and then when x is between 4 and 7, positive when x is between 2 and 4, and when x is greater than 7. Okay? So although we're not given information about the second derivative at 2, at 4, or at 7, we can probably safely conclude that if the first derivative is 0 at x equals 2, then we should have a point of inflection for x equals 2. Okay. All right, so now, based on this information, I would say that you should just put these same numbers down, 0, 2, 4, 5, and 7 for the final function number line. And then that way you can sort of consolidate these two pieces of information together. So here we have the function is increasing, then increasing, increasing, decreasing, decreasing. That's based on f prime. Okay? And then we know that the function will be concave down throughout, okay? And concave up, concave down, concave up. I do this part here, so just to be clear, this is concave down, concave down, concave up, concave down, then concave up. Okay? So now, based on this information that we've put together here, we should be able to come up with a somewhat accurate sketch of what this function should look like. And based on the fact that we're changing, let's say right here from concave down to concave up, and we have a point of inflection, then here concave up to concave down. So I can maybe assume that there's another point of inflection here. Okay. And then over here as well, from concave down to concave up at x equals 7, another point of inflection. Okay. Going back to what this interval is, we don't know because it wasn't specified. So really, you sort of have the option here of either having the function increase or decrease. So the sketch can look one of two ways. So I'm just going to sort of mimic the exact same intervals here, 2, 4, 5, 7. Okay. The last piece of information that I was given is that f of 0 is equal to -4. So I should plot that point down here-ish. It's just a rough sketch. Nope, there we go. So now I can sort of connect my points into a possible sketch of the function. So here I go, concave down up to 0, okay? And then here I still have concave down until 2, so let me go, let's say, up to here, concave down, okay? Then from 2 to 4, it should be concave up and increasing. And let's say right around here, like so. Okay. Then from 4 to 5, increasing and concave down, and I should have a local maximum, like so. And then from 5 to 7, the function is concave down. So let me put a point right here, let's say, concave down, like so. And then from 7 onwards, concave up. So this is one possible sketch of my function. I decided that my function from 0 to 2 would be increasing while it's concave down. So this is one possibility. Another possibility is that you could instead change just this part of the graph a little bit and maybe assume that you have a local maximum at 0, -4. And then that way you are going to end up having your function increase, then decrease, and then follow the rest of the same way. Okay. So another possibility would have been, let me just do this in pink. So this part would still be the same. And then instead of going up, it would go down like so. And that way we still have concave down from, well, when x is less than 2. And then at this point, you would then increase back up to the point of inflection at x equals 4. So this is another possibility just based on the fact that we weren't given enough information about this interval. And that's it. So let me just label here. I have a local maximum. And then just keep in mind, because we weren't told what this interval is, that's why we could assume that this x equals 2 point is either a local minimum. If it was negative, positive here, then this would be a local minimum. Or we could have also assumed that it's just a point of inflection, and in which case this original graph that I drew would match that. Okay.